diagram. And the question is, where is the thread? The one that's dropped obviously is going to hit the X below. But the one that has the thread that's wound up, where is it going to hit relative to X? That's the question. So I just want you to think about it and come up with like a knuckle-related answer. Everybody understand the situation? I want to know where that spool is going to hit. And it's wrapped up compared to the X below, straight below that. And you let them have a conclusion or a hypothesis.
Pulled out the old wheel.
Okay. Have a conversation. Compare and contrast.
Then from the center of mass.
Because you can think of it like you said, it's like a slope. So it's like down the wall.
There's no
Just
horizontal
down.
component.
It's
The
like
torque
straight.
is not doing any lateral work. It's doing vertical. Really?
Yeah, exactly.
The stapler. No. It's about a guillotine and stapler. I should have put it over there.
Everybody got something?
Yes.
Here we go. Nailed it. Okay.
Yeah.
Why?
The center of mass only has torque, tension upwards and gravity downwards, and no horizontal mass.
Right. There were no horizontal forces acting on the center of mass. Therefore, the center of mass will accelerate just in the y direction, just vertically. Good with that? Okay. Okay, go to 6. Jump a little bit there. All right, go to 64. Okay, so what for in this conversation? So, is student 1 right? What is wrong with student 1? Which part of the explanation is like, are you kidding me?
The force does not.
Right. Force. So the force does not affect the acceleration. So that is a jump. No matter where it's acting. What about 2? Do we agree with student 2?
No.
Why not? What's wrong about their explanation?
Because the force isn't used up in rotational acceleration.
There's no such thing as using up force. You can use up energy. You can't use up force. Do we agree with student 3?
Yes.
Yes. Student 3 is on the ball. Good with that?
Yep.
Okay. Is mechanical energy being conserved?
No.
This descends.
No. No.
Have a conversation.
There's torque in
Come on,
force.
Issue.
The torque is an external force.
Yeah, intention's good for it.
No, it's
Tension
the concept.
is the same thing as a wheel.
Well, if you look at the center of mass of the graph, you look at the center of mass, the
Parallel
torque,
to direction.
yeah, the force is applying work up in the negative direction. While gravity pulls it down.
No,
If that be true for static.
energy should be conserved, right? Because the energy that's not going into translation is going into rotation.
Yeah, they should have said.
Yeah, they're opposite something, like tension, it's not moving direction, pulling about it. So if you guys, yeah, I would say it's
The big
Yeah,
thinker.
the rope isn't doing the thing.
It's doing.
It's not applying any sort of force over any.
Is mechanical energy conserved?
Yes.
Thumbs up, thumbs down. Find someone that has the opposite thumb as you and have a good intellectual conversation.
I wasn't. I'm not completely.
they do their separate. Gravity is technically split.
The force of the distance. That's not.
They can't really cancel out.
Plus the problem is
Which is on the center of mass.
Yep.
So.
Not doing
It's parallel to direction.
Start at the top. Potential energy of gravity plus work on the surface translational and rotational. So how do you get this?
Like how it's falling.
Energy
You have non-conservative forces.
lower.
Even though it's canceled out by gravity, gravity is a
But what gets it to
You're
spin
taking
is
the work
that
of non-conservative forces when you're talking
Yeah,
about
but any
translation.
energy that
It's
isn't
only
going
non-conservative.
the translation isn't
That's what my
going.
word.
What is
tension?
the definition of work done by tension?
No, that's not how this is.
Yes.
it doesn't feel like the center of mass. Oh,
Objects falling downward versus tension is.
Okay, correct answer is thumbs up, thumbs down. Mechanical energy is conserved.
I think it is.
Mechanical energy is conserved. Just like friction acting on a ball rolling down an incline is acting on the object. But it's not causing displacement at that point. The tension, there is a force of tension, but it's not causing displacement at that point of contact. It's not doing work. It is a non-conservative force, yes, but it's not doing work. You okay with that? Okay.
For it to not be conserved, the school has to move out.
Yeah, if I were lowering it, or if I was doing that, then it would be doing work. Tony.
So force is independent of the time contact of work is independent.
I don't understand your first. Force is independent of the force of contact. Help me out.
Like, it's still applying the same speed as off the center of mass.
Yes. It affects the center of mass the same.
But you could, like, if it's off the center of mass, then it's not good.
No, that's not a good condition. It's if the point of contact is translating, is moving translationally. Translating, that's not a good. Is moving, like if there's displacement at the point of contact. Are you okay with that? I mean,
There were like a real school where the thread is heading closer to the center.
ooh, no, it would still be conserved because all you're doing there is changing the moment of inertia.
Is it changing like how far from the center the
You are changing the how far. You'd be changing the tension. That's what really you'd be changing if we're going to assume that the thread is massless in compared to the spool and not very thick compared to the spool. So you'd be changing tension because
it was still like a massive stream, but it just as it unravels, it gets closer.
right.
What do you mean by there's no displacement at the force of contact? That point of contact.
Good question. Hold on. Power. So just like there's no displacement where the friction isn't, like here, there's no displacement here. Like it's. Here's the ramp. Here's the ball. It's going. So it's not moving. It's not experiencing displacement here. It's not like slipping. Here, the spool, the molecules of the rope and the spool. Boy, that's harder to. Don't look at it like that. This is rolling down a string, just like this is rolling down a ramp. You okay with that? Okay. All right. So here's the scenario. Box. With the same mass as the spool. Suspended by height h. So equal heights, equal masses. But this one goes over a pulley that has mass. And the other end is attached to a box with a different mass, frictionless surface. Box is released from rest at the same time the spool is wrapped around it. The tension experienced by the suspended box is identical to the experience experienced by the spool. So this right here, this statement here is very fabricated. I magically made that statement true. Okay, like I doctored the situation, and I'm not saying it's impossible. I'm just saying super special case that I just like, boom, there it is. They have equal tensions.
What
Yeah.
was the example when mechanical energy wasn't concerned with the strength?
If I lifted, this would be positive work done by the tension. If I did that, where the center of mass was, that's bad. Where there was this point here was moving, had displacement at the moment of time it was in contact. Like there's a change in location of this right here where this is contacting. There was motion, displacement, causing work. Grab that. questions? So you're answering these, you're answering, which one's gonna hit the ground first? Definitely have a hypothesis. Okay, if and when you get questions like this, like student one, student two, student three, the last thing you want to do, a fatal flaw for these type of questions would be to start reading the question, start reading the responses before you come up with a conclusion. Does that make sense? You need to have something you need to have an answer to what it should be, because there's a lot of jargon in there that as you read, you might be influenced. Because these are popular answers. The people who made these tutorials interviewed like hundreds of college kids. Why do you think this is? And they compiled these. These were like the popular answers.
So these smart college kids that don't get it wrong.
Not smart college.
Okay? So, let's do this. Have a conversation amongst yourselves. Which one's gonna reach the ground first and why?
Because, yeah, if you look at the free body diagrams,
Insane about inertia to get it going.
gravity would definitely. Yes.
Fully has a moment of inertia.
Okay, so we got that, now we can ask all previous students. None of them.
That's true, they have the same body diagrams.
I guess that's right. Yeah, no, that's right. I did not read the last part, that sucks. No, I don't like it.
I mean, I don't like it.
Just because this acts
Yeah.
on
I guess
doesn't mean anything for the
We don't really want to look at the energy, we look at the forces upon them, so.
Why
But-
not? Oh,
Yes. But student two is like kind of yapping about energy, and then he's like, okay, both the same forces acting on them. So it's like, okay.
Okay, what do you say? Who reaches the ground first?
Same.
Same time. Now, what I want you to do is I want you to evaluate not their answer, but their explanation, what's wrong. Obviously, like school one is gonna be going faster, that's wrong, but like what's wrong with their explanation, student one?
I don't know what he's saying. He thinks the rotation is causing a type of greater speed.
It doesn't say that at first, it says we go faster when it's
Faster. True, I think they're implying that there's their center of mass is moving faster, therefore it's gonna hit sooner.
Yeah, so the string isn't causing the spool to pivot downwards, it's just by rotating the spool and with gravity to pull it downwards.
I mean, it depends on how you look at it. The tension is making it rotate, but it's not driving it downwards. It's actually preventing it from falling. Causing it to rotate, yes, but it's not like in my childhood, I played with those and let it go, you know what I'm talking about? It's not doing that. Okay. Old school top, I don't know if you know old school top, like, I don't know. Anyway, okay, student 2, wrong. Student 2, no, sorry, student 1's wrong. Student 2, what do we say?
Still
I don't think so, no.
What do we disagree with student 2?
The box's mechanical energy isn't conserved because the force tension is actually doing work and displacing.
If we define the system as just the box, tension is doing negative work. You doing okay with that?
It's just the free body diagram of the center of mass.
The spool, mechanical energy is conserved. But the box, just the box by itself, just this, that mechanical energy is not conserved. What would have to be true if the box's mechanical energy by itself was conserved? Sorry, the box Earth system. I always never put Earth in there.
It would be faster than the spool.
Yes, true. What would be the scenario for mechanical energy to be conserved? Right, no tension, dropping, free fall. That mechanical energy of the box would be conserved. Josh?
How, this might be a dumb question, I don't know, how do they both hit the ground at the same time? Because I feel like you either don't know that, or it's just like you don't know if the mass is off.
You do, okay, the masses are the same. So just this, the normal free body diagram, they are identical. They have the same mass, and I fabricated this idea they have the same tension. Therefore, their net force is identical, and they have the same mass, therefore their accelerations are identical.
But I just thought that because the one has to move the block as fast as well, so that would power mass the system.
Okay, yes, that's true, but that's not very, you are trying to be physics lawyers. You're trying to come up with a rock solid, cannot punch holes in this case. Is like, there's no fuzziness, there's no like, gray, this is like, this, black and white. This is true, this is true. Saying, well, this compensates for that, I'm not saying you're wrong, but that's not very definitive. Like, how do you know that this compensates exactly as much as that? That's a hard argument. But if you know these forces are the same and the masses are the same, then you can say acceleration is the same distance, it's going to hit the ground the same amount of time.
Yeah, so hypothetically, like, so the tension, if the tension's the same with one on the circular thing,
Yep.
that one's be moving upwards, because it has to be moving more than, like, with the other string light, had to be moved further than the other one.
Are you talking the questions we were doing the other day with the unraveling?
Because it's further away, so that way it has to be
Okay.
being pulled. It's still the same tension, but it's being pulled quicker.
Those are, okay. Okay, pitch that to me again.
So the tension on the circle
On the spool?
is being like, I don't know, so there's a machine back that's like pulling the string up while
Okay.
the ball is rolling down
Yeah.
to match the tension in the block.
It wouldn't have to pull it up, it would just hold it. You wouldn't have to reel it up. You could just pin it. If you had a machine that was roll it up, then I'm trying to like entertain your thought of the machine rolling up. Machine rolling up would have to follow this along, so this would continue to drop. That's the only way that would happen. Okay. All right, good conversation. Done with that tutorial. Student 3 was not right. Student 3 said box is going faster, the tension from the string causing the spool to rotate, giving it rotational kinetic, thus taking away from its translational kinetic energy. Boxes. Okay. All of that is not wrong. It's just the fact that the mechanical energy of the box is not conserved. That's where his downfall is. Student number 3. Yeah.